So we wrapped up chapter 2 on derivatives, and now we're going to talk about chapter 3, which has to do with all the different ways that we can apply derivatives and use them to help us find out more about different types of functions. So we're going to very briefly return to chapter 1, that was our limits chapter, and see why the derivatives can help us to evaluate limits that we can't really just do directly using direct substitution. I alluded to this many times when we were first talking about limits and said, oh, this is going to be a lot easier once we know how to take derivatives. Well, this is it. Okay, so as a review, if you wanted to take the limit of something like this is a rational function, 12x squared over 5x plus 2, and you want to take the limit of this function as x goes to 0, we're looking for the behavior of the function near 0. And so usually the first thing that we would do is we would use direct substitution. In other words, we would plug in x equals 0, and if we get a real number, then we're done. That's the limit, right? So we have 12 times 0 squared over 5 times 0 plus 2, which is 0 on top and 2 on the bottom. 0 over 2 is defined. That's a real number. It's just equal to 0. So this limit does exist, and it's equal to 0, and direct substitution was enough in this case. But remember that a lot of the time, most of the time, direct substitution was not enough to find the limit, right? So if we tried to use direct substitution here, right, we would get on top, we would have 0 squared plus 5 times 0, 5 times 0, and on the bottom we would have 3 times 0 squared plus 2 times 0. Of course, this is 0 over 0. Now remember, we call this an indeterminate form because when you use direct substitution and you got 0 over 0, we don't really know yet whether this limit exists or it doesn't. It could exist, it could be a finite number, it might just not exist, or it might be an infinite limit, right? It might be a vertical asymptote. And so this is what we call an indeterminate form. Now we had different ways of dealing with those when we went over the limits chapter. In this particular case, probably what we would do is we would factor it and cancel out the common factor of 0 and try again. But now that we have derivatives, there's actually a new way that we can evaluate a limit with an indeterminate form 0 over 0, and we call it L'Hôpital's rule. It looks sort of like Le Hospital, but I think it's French, and it's pronounced L'Hôpital. So L'Hôpital's rule says that if we suppose that for some functions f and g, direct substitution of the limit as x goes to some value a of f of x over g of x gives you an indeterminate form 0 over 0, or if it gives you an indeterminate form of some infinity over another infinity, either both positive, both negative, or one of each. In other words, if we're in a situation like this up above, or if we're in a situation where direct substitution gives you infinity on the top and the bottom, then L'Hôpital's rule tells us that the limit as x goes to a of f over g, right, this limit that we're looking for, is actually going to be equal to the limit as x goes to a of f prime over g prime. Okay, so in other words, what we're saying here is if direct substitution gives you either 0 over 0 or some infinity over another infinity, it doesn't even have to be the same infinity, then try taking the derivative of the top over the derivative of the bottom and take the limit again. L'Hôpital's rule tells us you're going to get the same limit. Now, one thing to notice here is we're not saying just take the derivative of this function f over g, because if we were to actually take the derivative of f over g, we would have to use the quotient rule, and the quotient rule does not give you this. It doesn't give you f prime over g prime, right? So this isn't as simple as saying if you get an indeterminate form 0 over 0, then just take the derivative and try again. It says specifically take the derivative of the top over the derivative of the bottom, right? So just as a little remark here, this is not the quotient rule. We're just taking the individual derivative of the top function divided by the derivative of the bottom function. We're not taking the derivative using the quotient rule. So let's see how this is useful for us, and why this is useful for us, with a couple of examples. So first we're going to try to take the limit as x goes to 0 of x squared plus 5x over 3x squared plus 2x. This is that first example that I talked about. We already saw that direct substitution gives you 0 over 0. And so by L'Hopital's rule, we know that the limit of this function is going to be equal to the limit as x goes to 0 of the derivative of the top over the derivative of the bottom. Right, so the derivative of x squared plus 5x would be 2x plus 5, and the derivative of 3x squared plus 2x would be 6x plus 2. Right, L'Hopital's rule tells us these two derivatives are the same. Okay, so can we use direct substitution now? Does it work? Actually, yeah, it does, right? If we were to plug in x equals 0, we would get 2 times 0 plus 5 over 6 times 0 plus 5. Oh, sorry, my bad. It's 6x plus 2 on the bottom, not 6x plus 5. So this should be 6 times 0 plus 2 when we use direct substitution. Okay, so this is 0 plus 5 on top, which is 5, and 0 plus 2 on the bottom, which is 2. So this limit is 5 over 2. Right, this is probably quicker than using our original method that we had here of factoring and canceling. Maybe, maybe not, I don't know. But it's just a different way of doing it. And it works because we had this indeterminate form of the type 0 over 0. So let's try another one where we have a different type of indeterminate form. All right, so we have the limit as x goes to negative infinity of 4x cubed plus 7x squared minus 12 over negative 5x cubed minus 4x plus 2. All right, well, we can't really direct substitution negative infinity in here because it's not a real number, but we can take the limit of the top and the limit of the bottom, and if that gives us a negative infinity over positive infinity or some sort of infinity over infinity, then that will be an indeterminate form. And that's exactly what happens here, right? As x goes to negative infinity, we know that any cubic function with a positive leading coefficient is going to go to negative infinity. And in the bottom, we've got a negative cubic function, right? A negative cubic function looks like this. So as x goes to infinity, the denominator is going to be going to positive infinity. Right? It doesn't even really matter whether it's positive or negative infinity on the top and the bottom. It's just the fact that the limits on top and bottom are both infinite. So this is an indeterminate form of the type infinity over infinity, so L'Hopital's rule applies. Okay, so we've got, according to L'Hopital's rule, I don't feel like writing it every time, so by L'Hopital's rule, this is going to be equal to the limit as x goes to negative infinity of this same function, but we're going to take the derivative of the top over the derivative of the bottom. So the derivative of the top would be 12x squared plus 14x, and the derivative of a constant 0. On the bottom, we've got negative 15x squared minus 4, and then the derivative of 9 is 0. Okay, so now again, we check to see, does this derivative exist, or do we get an indeterminate form? Well, on top, we've got a quadratic equation, x squared, and as x goes to negative infinity, this is going to be heading towards positive infinity. On the bottom, we've got negative x squared function, so this is like an upside down parabola. As x goes to negative infinity, this is going to go to negative infinity as well. Okay, so again, we have an indeterminate form of the type L'Hopital's rule. Right, this is an indeterminate form of the type infinity over infinity. But you know what? That means L'Hopital's rule is going to apply again. Type infinity over infinity. So L'Hopital's rule applies again, meaning we can just take the derivative again and just keep repeating until we get a determinate form, until we get an actual limit here, or until we get to a point where we can determine that the limit doesn't exist. So we're going to use L'Hopital's rule again here. Take the derivative of the top and the bottom. It'll be equal to the last limit, which is equal to the original limit we're looking for. Okay, the derivative of the top would be 24x plus 14. The derivative of the bottom would be negative 30x. That's it, negative 30x, because the 4 disappears. All right, as x goes to negative infinity, what's happening here? Well, the top is a linear function that's heading towards negative infinity, and the bottom is also a linear function that's heading towards, this time, positive infinity because it's got negative slope. So once again, it's an indeterminate form of the type infinity over infinity. So L'Hopital's rule still applies, right? We can apply it one more time. L'Hopital's rule applies. So once again, by L'Hopital's rule, this is going to be equal to the limit as x goes to negative infinity of 24 over negative 30. Derivative of the top function is just 24, the derivative of the bottom function is negative 30. Now there's no x values in this function anymore, this is a constant function, and so it doesn't really matter where you're headed. The derivative of a constant function is just, or sorry, the limit of a constant function as x goes to anything is just that constant. So it would be, if we reduce this, they're both divisible by 6, so 4 over negative 5. That's our limit. Okay. Now, if we think back to when we actually did this limit chapter, when we took limits at infinity, we had this sort of trick of comparing the degree of the top and the bottom and seeing if the degree was the same or if it was bigger on top or bigger on the bottom. When the degree was the same, we said that it ended up having a horizontal asymptote, meaning that limit ended up being the leading coefficient on top over the leading coefficient on the bottom, 4 over negative 5. That's exactly what we got. So this is just sort of a good check. And probably L'Hopital's rule isn't the best way to do this, but it is a pretty quick way because it's easy for us to do derivatives of polynomials. So it's quicker maybe than doing what we normally would have done, which is multiplying the top and the bottom by 1 over x cubed and then doing a bunch of cancellation. All right, so that's the second example. Let's just do a couple more, and then there'll be a worksheet for you to practice some more of these L'Hopital's rule problems. So this time we're going to take the limit as x goes to 1 from the right of the function 2x minus 2 over ln of x. Now, I know that we always forget what ln of x looks like. Ln of x looks like this. This is okay, so this is our ln of x function. What happens when we try to use direct substitution here? Well, if I plug in x equals 1, we're coming from the right, but it doesn't really matter here if we're just trying to figure out if it's an indeterminate form or not. Then we'd have 2 times 1 minus 2 on top, which is equal to 0. And on the bottom, we would have ln of 1. All right, ln of 1, right, the output when x is equal to 1 is also 0. And so we get an indeterminate form of the type 0 over 0. Okay, so what this means is we can use L'Hopital's rule. L'Hopital's rule applies. And so this is going to be equal to the limit as x goes to 1 from the right of the derivative of the top. So the derivative of 2x minus 2 is just 2, divided by the derivative of the bottom. ln of x has a derivative of 1 over x. We learned that in the last section. Okay, so what happens if I try to take this limit as x goes to 1? Well, direct substitution is going to work here. I can just plug in x equals 1, doesn't really matter that we're coming from the right, and I'm going to have a limit of 2 over 1 divided by 1, or 2 over 1, which is just equal to 2. So this limit exists and it's equal to 2. Okay, that was our third example, and for our last example here, we want to take the limit as x goes to infinity of e to the x over x cubed. Okay, as x goes to infinity, e to the x is the exponential function. The graph looks like this. And we can see that as x goes to infinity, this function is growing quickly and shooting up towards infinity. So the numerator approaches infinity, and the denominator, okay, x cubed looks like this, also is heading up towards positive infinity. So we get an indeterminate form of the type infinity over infinity, indeterminate form of type infinity over infinity. So L'Hopital's rule applies. So we can take the derivative of the top over the derivative of the bottom. and that'll be equal to the limit as x goes to infinity of the derivative of e to the x is e to the x, the derivative of 3x squared, the derivative of x cubed is 3x squared. Okay, now this again is going to give you an indeterminate form of the type infinity over infinity, because e to the x is heading towards infinity as x gets big, and so is 3x squared. So L'Hopital's rule applies again, and it's equal to the limit as x goes to infinity of the derivative of e to the x, the derivative of e to the x is e to the x, the derivative of 3x squared is 6x. Oof, again, it's going to infinity over infinity. Right, e to the x goes to infinity, and the linear function 6x goes to infinity. So we take the derivative one more time, and now we have, right, using L'Hopital's rule, we have this is equal to the limit as x goes to infinity of the derivative of e to the x, which is e to the x, divided by the derivative of 6x, which is just 6. Okay, now finally this is not an indeterminate form, because the numerator is heading towards infinity, and the denominator is a constant. It's just heading towards 6. Right? As x goes to infinity, 6 goes to 6. Right? So this function, e to the x over 6, is really just the function. We could write it as, for example, 1/6 times e to the x. It's just a constant times e to the x. And that's not going to affect the limit as x goes to infinity. It's going to grow towards infinity just slightly slower than e to the x does, but this limit is still infinite. Okay? So notice that when you use L'Hopital's rule, sometimes you have to use it many times, and also sometimes in the end you'll get to something that's not even a real limit, right? If the limit is infinite, technically the limit doesn't exist. So L'Hopital's rule doesn't guarantee that you'll get a finite limit at the end. It just gives you a way of getting there. Now again, this is a type of function that we had talked about in chapter 1. We said if you have an exponential function on top and a polynomial function on the bottom, exponential functions grow much, much faster than any polynomial function. So I had said this limit is going to be infinity because the top is going to be getting a lot bigger than the bottom. And when you have a really big number divided by only a sort of big number, the bigger number on top wins out, and this entire function is going to be heading towards infinity. But now we can use L'Hopital's rule to justify that and to see exactly why it's true. So you should try the more examples of using L'Hopital's rule in the worksheet for this section.